we had started looking at dipoles. So if we come back just a little bit, we finished talking about field lines, and again, the idea of them is to just show you the shape of the electric field. It's an invisible thing surrounding charged objects, and what we've done by using the idea of test charges and holding them up and seeing what happens and plotting that out eventually gets us to this picture of field lines. They are making that invisible field visible to us. And we started looking at combinations of point charges. We know the field for a single point charge is k times the size of the charge over the square of the distance from it. Now we're using that as a building block for things like dipoles. If you add the field of a positive and negative charge together, what does the overall composite field look like? And we found it everywhere along this line right here. And the main takeaway is that as you get farther away, the strength of that electric field dies off as the cube of the distance, which means if you get twice as far away, it gets 8 times weaker. The reason that's important, someone asked me applications of dipoles. I mentioned antennas. Another one is batteries are essentially electric dipoles. They're a separation of positive and negative charge, so like a C battery or AA, AAA. But then think about that for a second. This is something whose electric field dies off very, very fast. And yet, you connect a battery up to something, even if it's really long wires, it puts the thing you're trying to power pretty far away from the battery. That doesn't really affect it. So what's that about? Well, we'll find out in a few chapters. But now we are asking the question of, if I put it in an outside electric field made by something else off screen, what will the dipole do? And we had started looking at it. We said the positive charge will be pulled along the field. The negative charge will be pulled opposite the field. And so the net force on the dipole is 0. But that's related to the acceleration of the center of mass is the technical term. I'd say just think of, and in this case, if they're equal amounts of mass on both ends, both positive and negative charges are the same mass, it's right in the center. But think of it as just the whole dipole is what I'm really trying to describe the motion of here. So if the net force on that dipole is 0, then the acceleration of its center of mass is 0. And what that means is, if the center of mass is not moving at first, the dipole is stationary at first, then the center of mass can never move because it can't gain speed, it can't accelerate. So the center of the dipole can't move. Now, if you gave it a kick, you push it, it can move. In that case, it just won't speed up or slow down in this electric field. It'll just sort of drift. But that really means this thing is kind of pinned in place at the center of mass. Like, actually imagine you put a stake down in the middle and you balance your dipole on top of it. It cannot shift from that point. What it can do, though, if that point is fixed and yet we're pulling on this side and pulling on this side, what's the dipole going to do? Let me ask a similar question. This is a very poorly drawn steering wheel. It's pinned at the center. It's fixed. It cannot shift left or right. But if you pull on the top and you pull the other way on the bottom, what does your steering wheel do?
It rotates.
Yeah, and in this case, clockwise. That's what the dipole will do. It will rotate. It's pinned in place. It can't shift or translate left, right, up, or down, but the whole thing can rotate. So that is a torque on the dipole. And it is not 0. So in this picture, these forces will make the dipole rotate clockwise. That's the torque on the dipole. We're going to find out how large that torque is in terms of how strong the field is and how big the charges are. So just stop and confirm to yourself that makes sense that it should depend on those things. If we crank up the strength of this electric field, that's going to crank up how large these forces are. And that's like pulling harder on both ends of your steering wheel. It'll rotate faster. That's more torque. If it's bigger charges, again, they will feel a bigger force from that field. And so they will rotate faster. That makes more torque.
If the charges are closer together.
Yes, there we go. So the spacing of the charges matters. Why? Well, remember how torque works. Think back to opening a door. If you push on the hinge, that door's not going to open even if you push really hard. If you push near the doorknob, the edge of the door, it'll rotate just fine. So how far apart the two charges are, and in particular how far they are from the center of mass, the rotation point, is going to determine how much torque you get. The wider the spacing, the more torque, because it's like you're moving towards the edge of the door in both directions. Think of it sort of like a revolving door. You don't have to draw this part because it's just messy, but this is like a top-down view of a revolving door. If the door is wider and you push on it, it will rotate easier. So yeah, that spacing is important. And we're going to see all three of those things pop out. How big the charges are, how far apart they are, and how strong the electric field is all determine the torque. So let's start analyzing. So the net torque on the dipole is going to be the torque on the positive charge and the torque on the negative added together. Anyone remember how we find torque? It's the thing that tells you how effective a force is at causing rotation. So it depends on how large the force is. You push harder, you can open a door easier. It depends on the orientation of that force relative to the door. I'll label that in this picture in a second, but if you're pushing perpendicular to the door, you're pushing how you normally push as a human being on a door, it opens easily. If you try and push long ways on the door, like you're pushing towards the hinge, that door's not going to open and you'll look like an idiot. So the orientation of the force matters. And then lastly, that thing we mentioned about how far you are from the axis of rotation. So orientation of the force and your distance from the axis. And I could even pop in a little plus and minus. This is just the convention for torque. Negative torque is one that causes a clockwise rotation. Positive torque is one that causes a counterclockwise rotation. It feels backwards, but that's just how we do that. So in this picture, let's get those signs correct first. SIGN. What kind of rotation does this torque from the electric field cause?
Clockwise.
Clockwise. So negative, and then also negative for the negative charge. So it's negative and then some other stuff. And then plus negative and then some other stuff. We'll fill that other stuff in a second. All right, next thing is the force on each charge. And it's the same amount of force on each. And then we have to start worrying about angles. So this picture might get a little bit messy. We'll see. But I'm going to look at this angle right here. That's going to be the angle the dipole makes with the electric field, because that seems like a relevant thing to look at, how the orientation of the dipole with respect to the electric field. And then I'm going to try and bring that up here to my force and break it into components. One that is along the dipole and one that is perpendicular to the dipole. Well, in that case, this angle right here is also theta. That's just because it's essentially the same two lines I'm comparing the angle between. They point in the same direction. But if that angle is theta, this component of the force pulling on the positive charge is F sine theta. It's opposite that angle theta. And that's the part that actually matters to rotate the dipole. This part is like pulling away from the hinge of the door in this case. Like you're standing on the side of the door and you're trying to yank it off its hinges. Stupid if you're trying to open that door. This is the one that's like pulling on the doorknob. It'll open it. It'll make it rotate. And that's what we have down here. F sine theta. And very similar analysis for the negative charge. Break it into components. This angle is theta. This component is F sine theta. So same thing for the negative charge. And now we need the distance. So if these charges are of equal size, then the distance is just the midpoint. It's d over 2. If they're not of the same size, it'll be towards the larger mass charge. And so I'm going to keep it sort of generic like that. I'll say, let's call this distance to the positive charge x. It's an unknown. It depends on how much mass the positive charge has compared to the negative. But then that makes this d minus x. And those are the distances that those two forces act, the ones pulling on the negative and positive charge to make the dipole rotate. That's like how far you are from the hinge of the door, where the doorknob is. And that's the last piece that goes in here. It's x for the positive charge. That's how far away the force acts on the positive side. And then d minus x for the negative charge.
And it's negative because it's spinning clockwise, right?
Yes, correct. So
Okay.
good note.
So can you just go over that one more time? Like,
Yeah, I needed to figure out, all right, where do these forces act compared to the axis of rotation? The force on the negative charge acts a distance d minus x away from the center of mass. The force on the positive charge acts a distance x away from it. That's where I got these things. I also need to worry about the orientation of those forces. So which way do they point compared to, just think of along the door. So I only need F sine theta on both sides because that's the only part of the force that actually rotates the whole dipole. The other component, which would be F cosine theta, it just stretches the dipole out. It's trying to rip it apart. And hopefully it's not very good at it, so it doesn't break the whole thing. But the main important thing to actually make the dipole rotate is the F sine theta piece. But what I notice is I've got negative F sine theta x, and then buried inside, if I distribute out that negative, it's a positive F sine theta x. So those are going to cancel each other out. So that thing right there is canceled. And I'm just left with negative F sine theta d. I could also write that as the force is the size of either charge, so the positive or negative, times the strength of the field they're sitting in, and then times sine of theta. And then that distance d, the dipole spacing. And finally, I could regroup. But what is this thing right here?
Is that the value of the charge and the distance?
It is. We gave that a special name on the last page. What's it called?
Dipole moment.
The
There we go.
dipole moment?
So, could write it as negative PE sine theta. And this is where the dipole moment is actually kind of important. So notice it shows up both in something telling us how a dipole will rotate in an outside electric field, and it shows up in something telling us about the electric field the dipole creates. So that's what I mean of it describes the strength of the dipole in both how it affects other things and how it is affected by other outside electric fields. It's something you can staple to that dipole and say, this one has a large p-value. It will both create a strong field and respond strongly to electric fields. it would rotate, I'm just going to say toward smaller theta. It's going to try and close that gap until what happens? When is the dipole going to stop rotating? This is where we get a low budget prop. Here's my dipole. There's my field beneath it. The positive charge is going to be pulled to the right. The negative charge is pulled to the left, but that's going to rotate the whole thing. The direction of that force is never going to change, though. The positive is always pulled to the right, even as it rotates. The negative charge is always pulled to the left. When is it going to stop rotating? Any thought?
Until it's parallel?
Until it's parallel, because now the force to the right and the force to the left aren't doing anything to rotate the dipole. They would just stretch it out. They would just try and pull it apart. There is no component left of the force that's trying to rotate the dipole once it reaches this orientation. If I keep rotating, it's even worse, because now the negative charge is still being pulled to the left, the positive charge is being pulled to the right. That's going to actually try and turn it back towards alignment. So that's what happens. If you're up here, it gets pulled towards alignment. If you're down here, it gets pulled towards alignment. The dipole always tries to line up with the electric field towards smaller theta. And that's another way to say the torque is negative. You remember in physics 1, you talk about restoring forces and maybe restoring torques for pendulums. It's something that tries to bring the system back towards equilibrium, back towards its sort of balancing point. The dipole moment and the electric field are both vectors. So there's something that you may be used to seeing written as vector A's magnitude times vector B's magnitude times the sine of the angle between them.
Isn't that cross product or dot product?
Yes, it is the cross product. So you could write this as a cross product if you're worrying about the torque vector, but we're never going to need that. Someone in a physics major may someday need that again, may see it again, so I feel obligated to mention it, but this is what you would use on assignments. And look, what it depends on. How much the dipole rotates, the torque, depends on how strong the field is, and then buried inside of P is how large the charges are and how far apart they are. All the things we said it should depend on. And then sine theta is the orientation of the dipole. That also matters. That's what we got going on over here. So when theta is at 90 degrees, the dipole is really going to want to rotate. That's max torque. Once it's settled in and lined up with the field, those forces aren't rotating anymore. They're stretching the dipole out. And so we get zero torque. And the reason the dipole moment is important, besides that it just sort of describes the strength of the dipole, is we defined it to point from the negative to the positive. The dipole moment vector also tells you when this is going to stop rotating. The whole dipole is going to rotate until that vector lines up with the electric field. When the vector pointing from negative to positive lines up, that's when we know this thing's going to stop and stay in that orientation. Torque is maximum when the dipole moment is perpendicular. Minimum when it is parallel, or in other words, the dipole moment tries to line up. With the electric field. I know at this stage you're wondering, what's the point? The point is, if you're lazy like me, you use this every single day without realizing it. So water acts like a dipole, and it's because of the oxygen part of the molecule having lots of electrons, and that tends to make the oxygen side of the molecule negative, whereas the hydrogen side is more positive. So oxygen side is slightly negative. Say I suddenly turn on an electric field, again from some outside unpictured thing, some very large positive and negative charges. What's the dipole going to do?
Spin until the positive is parallel with the negative?
Yes, I think it's just a wording thing. So it will rotate until the positive and negative have sort of swapped places. In other words, the dipole will flip over. And it's because the positive part part gets pulled along the field. The negative part gets pulled opposite the field. Those are the forces on both sides of the molecule. And so it will flip the whole thing over until hydrogen's down here and oxygen is up top. So this is the oxygen side. This is now the hydrogen side. Sajid, question?
Yeah, I just wanted to ask a clarifying question. That's because the electric field points the way that the protons would want to go, correct?
Yes, that's a good way to think about it. Yeah, the positive charge does what the electric field tells it to. Negative charge is rebellious. It does the exact opposite. And so what if we flipped this field back over the other way?
It would rotate back around to its initial orientation.
Yeah, so what if we come up with a way to flip-flop this field really fast? Back and forth, back and forth, back and forth. Well, then the molecule is going to start really jiggling, vibrating, and it'll be smacking into whatever else is around it. If something has a lot of water in it, you'll have this happening on a large scale, and that's going to transfer energy from the water molecules that they're getting from the electric field to the surrounding molecules. What is this? What do you have? It's a device in your house.
Microwave.
Yeah. Vibrates the water molecules really, really fast to heat things up, transfer thermal energy. This is how a microwave works. And it's also the reason why things that are very dry don't heat well. You can use paper plates and stuff like that in the microwave. Things that are very wet, have a lot of water, like soup, they come out the temperature of the sun. And also why they tell you for some things, some frozen stuff, to wrap it in a wet paper towel, so it is better at transferring that thermal energy. Like I said, if you're lazy like me, you use this almost every day. The rest of the chapter is calculus, unfortunately. So we're essentially going to be playing with Legos, but just in the least fun way possible. We're going to use our point charges as building blocks to build up more complicated things, and then find the field of those things using calculus by adding up all the little point charge fields until we get the overall electric field. So we're going to start by doing it with a ring of charge. We'll say it has a radius r, capital R, but we can think of it as a bunch of point charges placed in some kind of cultish summoning circle. If we add up each of their electric fields, we will get the overall field, so we have to figure out how to add up each of these individual fields. I'm going to say, compared to the overall charge on the ring, which we'll call Q, each little point charge has a bit of it, a dq of charge. So, for instance, this guy right here, he's got 1 dq worth of charge, a little bit of q, and that creates a tiny electric field at every point around it, a little dE. So for instance, in this picture, if I'm looking at this point P, it's a distance r away from that little charge. That is going to be important in determining the strength of the electric field. And that electric field at P is going to point which way if dq is a positive charge. Does it point towards or away from positive charges?
Away, so right.
Yeah, so it's off in this direction. And that's going to be one of my technically infinite dEs that I have to add together here. So that's going to be interesting to figure out how to do. So my little point charge, it creates an electric field of, I'm again going to use this instead of K, but they're the same number. And it's of size dq for the charge. And we're looking at the field a distance r away, right? So that's the field from just one single charge. Here's the first clever trick that I am not clever enough to think of, but someone was in history. Look at the exact opposite side of the ring. There's also a little positive charge over here of size dq. And it will also create a field at that point P, a distance r away. And that field will be the same strength and size, it just points in the opposite direction. So that's another dE. Look at just adding those two. So I've still got, again, infinitely many more to go, but I've figured out what to do with 2 of them right now, 2 of the charges making up the ring. Break it into components.
When they cancel?
Some of it cancels. Good call. What cancels?
The horizontal components of the vectors would cancel.
Yeah, they face in exact opposite directions. So they're going to cancel out. The vertical components are going to add together. So we get a net field just from those two that points upward. I'm not going to draw that one in yet, but we do know it's going to be coming from each of these components. And to call it a sine or cosine, I'm going to need an angle. I'm going to use this angle. So this will be my theta. And if that's theta, so is this. By geometry, those two angles are equal. But that would make this dE times what? Sine or cosine of theta?
Cosine.
Yeah, that component is adjacent to theta. So that's our vertical components. They're going to add together. And so to get the electric field of the ring, I really just need to add up all of these dE cosine thetas. The sine thetas are all going to cancel because I can do this pairing up everywhere around the ring. These two guys are a match, and then these two guys are a match, and so on all the way around the ring. This is the vertical component of the point charge fields. What do I need to do with those to get the overall electric field of the ring?
Add them up.
Add them up. But we're going to imagine they get really, really, really tiny. We shrink them down until instead of it looks like a summoning circle, it looks like a continuous ring of charge. And in that case, summing up means doing the integral over the entire ring, adding up all these things. Add up all those little components. And now I can sub in what I found to be the electric field for each of my little dEs. So constants can come out of the integral, and I'm left with dq cosine theta over r squared. And I got to add that up over the entire ring somehow. And this is a very new way for most people to see calculus because the physics way is very like fast and loose and playing around with differentials and things that mathematicians hate. And also, this probably looks not like any integral you've seen because it's all in terms of, in this case, three different things: charge, theta, and r. So we got to clean this up a little bit. I need to put everything in terms of a single variable. So let's focus on each of these. For any particular charge making up this ring, any dq, does theta change? So theta is again just this angle that it makes when you draw this line from the charge to the point you're interested in, and then the vertical. Is that a different angle for different dqs?
Yes.
It is? So
No.
like, look at those two. So here's that one, here's its theta, here's this one, here's its theta. Are those different angles?
No.
No, and if I went to this one right here, you can't see it in this perspective, but if I drew it, this is like a tint that I'm drawing in the middle, or a cone. So those angles should all agree with each other. Does that make sense?
It does now that I see it.
Okay. I mean, that's learning. If everything were right the first time, you wouldn't need me. And what about R? So that's how far that point of interest P is from every charge. Is that different for any of them?
No.
No, every single one of these charges is the same distance away from that point because they're in this weird summoning circle and it's in the middle. So they're the same no matter what. But that means they're actually not variables. They can come out of the integral too. So I pull out cosine theta. I pull out 4 pi epsilon 0 and r squared. Add up over the ring what's left, which is dq, all the little dq's. If I add up all the little dq's making up that ring, what do I get?
Wouldn't it be like the sum of the charges that
Yeah.
we were?
Yeah, it's the total charge on the ring. If you want limits of integration, think of it as I start with no q accumulated. I've not counted any of them. Then I count this one. So that's the first one. I count from 0 up to, I add one dq and then another dq and another dq all the way up until I'm at all of the charge q on the ring. So this is q over 4 pi epsilon 0 and then all the stuff that's left. So q is the total charge on the ring. And technically we're done. You could use this to calculate the electric field of a ring of charge. It's just still in terms of three different things, charge, theta, and r. So we want to clean up yet a little bit more. But now we just need trig, not calculus, to do it. So I'm going to redraw one of these triangles up here. I'm just going to sketch it down at the bottom. So it has a base of the radius of the ring. It has a height of how far up above the center of the ring that point of interest is, so where we want to find the field at. And we are again going to call that z, just like we did for the dipole. And then there's this distance r from any one of the little charges to that point of interest. So this is point P from the picture, and this is one of my little DQs making up that ring. This is theta, and this is that distance r. Now we're ready to do some trig. Yay. So I want to rewrite both r, and I want to rewrite cosine of theta. And really I actually just need r squared. How can I use these two things to write this?
Pythagorean theorem?
Yeah, that's all it is. R is the hypotenuse, so this is z squared plus r squared. All right, now I want to rewrite cosine of theta. How do you calculate cosine? It's what over what?
Z over lowercase r?
Yeah. So it's adjacent over hypotenuse, z over little r. But I just figured out how to rewrite little r. So I could also rewrite this as square root z squared plus big R squared. And now everything's in terms of just that variable z. It's the only thing that changes depending on what point you're interested in finding the field at. And in particular, this thing, if I use that information I just found, it's this divided by this, which, take my word on this, but cosine theta over r squared is going to be z over z squared plus big R squared to the 3/2 power. That's just what I get when I divide those two things. And now I can put that in for the electric field of the ring, and I'm done. Like, I'm actually done. All right, that is my answer for the electric field of a ring. This is where you got to do a spot check. Does this all make sense? So, does it make sense that the more charge there is, the stronger the field?
Yep.
Great. Now look at z. That's how far above or below the ring we are. So z is how far you are from the ring. What do you expect to happen if you get really, really far away from this ring? What happens to the strength of the field?
It weakens.
Yeah, it gets a lot weaker. Well, it's a little bit harder to see this, but it works. If z gets really, really big, this number almost doesn't matter because z is so much bigger than it. But z squared to the 3/2 power is z cubed. So you've got z divided by z cubed, that's 1 over z squared. That number gets smaller as z gets really, really big. It actually looks a lot like what it would look like for a point charge. And finally, if r, the radius of the ring, gets huge, what do you think happens to the strength of the electric field?
Gets weaker.
It gets weaker because now the entire ring, all the charges on it are farther away from that point you're interested in. All right, that works too because it's in the denominator. So we are actually done. We have a value for this. The one thing we could do is rewrite it because you see it written in terms of this a lot, in terms of what's called the linear charge density. This is how much charge is on the ring. This is the circumference of the ring. So length, but for a circle. That's why it's the linear charge density. What does that number tell you? What's it describing about the ring? Well, if it's a really big number, it's either because Q is really big or because this is really small. We're dividing by a small number. It's how much charge you're packing into the ring. It's the density of charge along that line, the ring itself. It's how tightly packed the charge is. And if we put that in, we get this alternate version. And the last thing I need to sketch in on the page is just what does the field actually look like? This will be a positively charged ring. And this will be a negatively charged. What do field lines do for positive charge?
They push.
Yeah, they point away. And all we actually know right now is the electric field along that center line. I never assumed a point could be off over here because then those distances to the two charges do change. So I actually only know things along that one particular line, but I know it should point away on both sides. And what I can tell you is if you do a more detailed analysis, the field elsewhere sort of looks like this. Sort of bends like that. It's like all the positive charges are trying to push away from themselves, but that means they get in the way of each other. There's the electric field of the ring. Or if you want field vectors, which I don't think you do, this is actually a negatively charged because they're pointing towards, but if I reverse charge, now it's positive. Field lines are nicer to look at. But what you notice is it actually looks a whole heck of a lot like two like charges. They fight each other. And it's because that's all a ring is. It's this just laid out in pairs all the way around the ring until you form the entire ring. So it should have that sort of symmetry to it. And the reason you should care at all about this is because you can do something really neat with it. We're going to talk about it on that last page. It's trapped ion quantum computers, but you can use a charged ring to trap charge. It can't escape. Now, you can't do it with just a fixed positive or fixed negative. You have to alternate it. So I'm going to come over to this. So it's pulling all of those charges towards it, but they can kind of drift off and fall out if they shoot through the middle. Let me do a little bit less of them. Okay, so they kind of just fall through the middle, and they don't come back if they're going too fast. But now watch if I start, I'll add a few more. If I start flip-flopping the field, and I'm actually going to make the ring bigger, so it's a little clearer, we'll show velocities, and do not quite as many of these. So if I keep reversing the field, I can hold the charges in place. And that's used in what's called an ion trap. So you need, for one kind of quantum computer, they trap charged particles, ions, and use the electrons of them as qubits, as the information bits for quantum computers. And the reason you need to trap them is so you get zero outside noise. It's floating in empty space. There is no interference from something else outside. And you need that or else it's very fragile to store information for quantum computers. Okay. The last thing on this page is just, here's the negative. It's the same thing, but reversed. Like that. I grant you, this is not fun. It really is boring. But this is how we use the point charge as a building block to find fields for more complicated things. It's the only tool we have at the moment to do that. Any questions? All right, well, if not, we do still have that quiz on Friday. It will finally happen, I promise. I know you were worried about it, but I'll see y'all then, and stay safe. If you can avoid coming to campus or at least wait till later, then do so, and have a good day.